quickly. It's difficult. That's the thing. If you go through the if you go through the kernel build and you look for there's a dummy stage during the build. Okay, there's a stage when the kernel's being built at which it effectively builds a program called dummy, and it does that in order to abuse the intended purpose of one of the tools to achieve something completely different. It wants to put all these different pieces of the kernel together. There's no standard way to do that, but there is a different tool that can roughly do what they want, so they call it in an unusual way, and they result in, the point is it's a hack. There's lots of hacks in there being used to put my kernel together for my machine. I want to finish at 9, so I'm trying to move along. Okay, so machine-defined hardware entry, yeah? Okay, so I'm going to get hold of this chip from IBM. It's a PowerPC processor made by IBM, and they're going to give me a data sheet. It's a huge piece. It's not a, data sheets are not single pieces of paper. Data sheets are 1,000 pieces of paper, roughly described as a sheet. If you're some kind of giant, I guess it might be. But the data sheet will say, okay, in order to build a kernel for this kind of chip, you have to do these things. Okay, so I have machine-defined hardware entry. There's a machine-defined way in which my machine starts. There's a defined way in which my Linux kernel must be put together in order for it to work on that machine. There are machine-defined interrupts. There's concept of a timer, something that's running 1,000 times a second, telling me, tick, 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 tick. That's done differently on different kinds of machine. I need to support that. I need to support virtual memory. I need to do a lot of things. And ultimately, once I've done all that stuff, I want to end up at a function in my kernel where it starts doing useful stuff. So there's a function called start kernel. That's really where the first bit of C code comes into things. So up until that point, we're in the guts of the machine. We might be doing a little bit of C programming, probably a lot of assembler, lots of scary stuff. We end up running some C code that starts off the first process in my machine, starts managing memory, starts detecting devices, starts making those devices available, gets my file system working, those kinds of things. But we really have a lot of stuff to do before we can even start the machine, really doing anything useful. So, luckily, we don't have to worry about that very often. We don't port the kernel from one architecture to another very often. There's a lot of things that have to change. We don't want to have to worry about that. What we do worry about is platform porting. So what's a platform? Well, broadly speaking, this is a PowerPC platform, and so is this one. Okay? This is a PowerPC platform, and so is this one. Okay? And there are several other PowerPC platforms sitting on those desks up there. Some of them might be Intel now, who knows? But these are all PowerPC machines, but they're not the same. They're not the same model. They're different arrangements of the components within the machine, but they are fundamentally PowerPC machines. So they share that. In common. They're based on a standard architecture. They're based on one of the 20 that we know of, that Linux already knows about. But they arrange things differently. They have different network adapters. They have different sound cards. They have different arrangements of the same components within the machine. What the hell's he on about? I mean, this doesn't make any sense. Well, let me try to make this make a bit more sense. TiVo runs on a PowerPC platform. Okay? PowerBooks run on a PowerPC platform. Okay? Industrial Linux is running on a PowerPC. GameCube Linux runs on a PowerPC. These are different platforms based on standard architectures. I'm kind of glossing over the fact that there are sort of sub-architectures here, but I'm not really going to worry about that. Fundamentally, we have different kinds of platform built on these standard architectures here. We take ARM as another example. there's a PDA going around I gave out at the beginning. It's a Nokia 770. It's based on an ARM processor. Okay. This iPod that happens to run iPod Linux, it also has an ARM processor inside it. In fact, it has two. You know, Apple didn't want to kind of scrimp on processors, so they put two ARMs in here. There's a Broadcom ARM processor inside this machine. Okay, they're all ARMs, but there are different arrangements of the other parts of the machine. Okay. I'm not going to get too worried about the hardware differences because I think we would be here all night if I did that. But fundamentally, you know, we have the same machine, we have different configuration of the other components within it. So, that's all very well. Let's say we want to get the Linux kernel moved from a machine we already know about. Let's take the laptop as an example. Let's take this one. I want to take Linux and I want to get it up and running on different kinds of a different PowerPC platform that shares things in common with this one. Okay. So we select a hardware platform. We select the processor, the architecture requirements. We select the memory, the storage, the other components within our system. We acquire the necessary tools. If we're doing hardware engineering, we're putting this together. We might need to have hardware debuggers. We might need to have various electrical test equipment and all that stuff. And then we acquire the necessary software tools. Okay, so we need to get hold of some tools that we can use to build Linux for our new device. So you need to get a tool chain. A tool chain is a group of tools that you can use to do these things. That includes GCC, but not just GCC. It also includes the other tools you need in order to take an application and build it for a particular kind of computer. So you can grab one from your distribution if all you're doing is building another kind of PC-like system. But if you're doing something a bit more interesting, you might need to build or find one. The standard one we use in the embedded space is Dan Kegel's Cross tool. And Cross tool, you go to his website, you download Cross tool, you configure it, you say, I want a tool that can build a kernel to run on processor X, Y, or Z, and it will do that for you. And if you really want, you can pay a vendor to give you a flashy tool with lots of GUI gloss that looks really cool and costs a few $1,000 as well. It's the same thing, okay? So this is the same as this, but you're paying a lot more for this one. So, do this one if you want, but you can also do the other one, So, get a good book, okay? So you need to understand the Linux kernel. I didn't write any of those. I don't have any vested interest in any of those. I am working on this one, so don't ignore anything I say about the second one. But you want to get a book. You want to get Understanding the Linux Kernel. That's a great book. That's kind of here's 1,000 pages. It may not be 1,000, but here's I didn't even get it out. It's too big. It's in my bag somewhere. It's a huge book. It kind of takes the whole kernel apart and talks to you at extreme length, longer than I've been talking tonight even, about how the system's put together. You can get Linux Kernel Development. That's a book by Robert Love. He's also based in the Boston area. That's a great book as well. That's more of a kind of higher level book. Talks about development concepts. Kind of leaves the rest up to you to figure out. Linux Device Drivers concentrates on writing drivers for specific kinds of device. So I want to write a sound driver. I've already got my Linux up and running on this board, but I would like to support this proprietary CAN bus in my CAN. You've probably never heard of it. No one has. It's a bus used in industrial automation. If I want to support that, I may need to write a driver for it, so I can read that book and write a driver for it. If you're working out in the embedded space, doing some more interesting, funky stuff, then building embedded Linux systems, it's already out there. That's a good book as well. Okay. So once you've got all the kind of prerequisites in place, what do you do next? You need to bring up the system. What do I mean by bring it up? Well, I mean bring it up by its bootstraps, get it working, get it to do something for the first time. Okay? So we need a firmware, we need some BIOS, we need something that's going to run on my machine and get it to the point where I can even use a Linux kernel. Okay? This is useless when I turn it on. It doesn't even know how to talk to its memory properly. Okay? When I turn this on, you know, it's got no caching support. It's not able to, it doesn't have any performance optimization. It has very, very little, minimal support, enough to load some code and run it, but not enough to really do anything interesting with Linux. So I have a piece of code. The reason I have a BIOS, the reason I have Linux BIOS, U-boot, Red boot, one of these things running. On a PC, I'll have a regular BIOS written by one of those companies you see when you turn your PC on. The reason you have that is your machine does not know how to properly talk to its memory, how to properly take advantage of a lot of the fundamental features it has until after they've been set up. Yes, it can load some code and run it, but can't do very much until this piece of code has come in there first. This piece of code also may support more than just getting the memory working, getting caching support turned on, these kinds of things. It might also be a load of file from a compact flash card in this case, or it might be able to find a file on a network, something like this, and boot it. Take a kernel from somewhere and run it. Or you might need an extra step in here on your PC. You know, you guys already have seen Grub, BLU, some of these tools. They get called by the BIOS. They're sitting on your disk. They get executed. Their job is to then come in and run the kernel itself. No question. Good. You might have to port the firmware to your device. You might have to get this firmware up and running. So you get your tool chain in place. You get your debugging tools in place. So you need to make sure you've got GDB. You've got the different tools you're going to need to fix things when they go wrong. And you spend a lot of time hacking code. A lot of time. I mean, you're looking at so going back to my MRI example or our NMR example, by the way, if you ever wonder why they use the term MRI and NMR, the reason is that people don't like the word nuclear. Okay, so we have MRI, which means exactly the same thing, but doesn't have the word nuclear in it. It's a lot more acceptable to people. That's why the term exists. Okay, so we have Linux running for our system. We want to get it up and running on our new kind of funky device. And when I started work on the previous project, we just had the hardware barely working. We had some problems with the memory. Every now and again we'd run some code and something completely different would happen because actually it was getting corrupted as it was being pulled in from the RAM. You know, you have to worry about things like that. Normally you take it for granted that the memory in your machine is working. And we went probably within 2 weeks of getting the tools and getting the basic system in place. We were able to start having the Linux boot process come up, start having messages coming out from our kernel saying, you know, I'm trying to do this, oh, panic, something went wrong, and then you start sitting there going through endless hours of debugging cycles. You know, and once you get to kernel build number, you know, 2000 and something, then you start to, you know, get somewhere. You're looking at thousands and thousands of rebuilds. But fortunately, we can cheat. I was going to say porting the Linux kernel by cheating, but I thought I probably shouldn't say that. Most systems are variants of existing ones. Okay, we don't tend to go out there and buy something that's so radically different from what we had before that it changes the world, despite what the marketing says. Okay, the marketing's going to tell you it's great, it changes everything. Well, it doesn't. It just adds the latest version of some device that you probably already had before. You probably already had a wireless chipset in your laptop. You got a new laptop, you had a new revision of that wireless chipset, yes, it adds some new capability, but